Hello there, my name is Chen Yujie, and my friends also call me Gabriel, because my Chinese name is quite hard for them to pronounce. I'm a fourth-year exchange student studying Technological University Dublin. I come from Nanchang, a provincial capital city in the south of the People's Republic of China. My final year project is to prototype a DSP development kit suitable for use in our programs. I very appreciate my project supervisor, Mr. Frank Duignan, for his help and guidance. This year will be remembered for the COVID-19 pandemic. Even so, Frank still keeps in touch with me via emails and online meetings. The main objective of this project is to develop a DSP kit that could remove high-frequency noise in a speech audio, and there are 5 parts involved. There are circuit designing, filter designing, PCB designing, implementation, and testing. The microprocessor I used in this project is called STM32G431. It is a Cortex-M4 based microprocessor made by STMicroelectronics and equipped with high-speed memories, 6 DAC and ADC channels, and standard communication interfaces. TDA1308 is a headphone driver with high signal-to-noise ratio, low power consumption, and excellent power supply ripple rejection. It is used to connect the microprocessor and audio output jack. It rises the low voltage signal from the microprocessor to a sufficient level so that it can be converted into sound waves by the speaker. CH340G is a USB bus convert chip. It can real-time convert USB data for a serial interface so that we can transfer data and filter designs between the computer and the kit. We can also set the DTR and RTS signals on the computer side. This diagram shows the system framework. The audio input first goes through a preconditioning and protection circuit. The processed analog signal will be converted into digital signal by the built-in ADC later. And a DSP algorithm is then performed to eliminate the high-frequency noise. After that, the audio's digital data will be converted back to the analog signals using the built-in DAC and output through a 3.5mm jack after being amplified by the headphone driver. The input signal may contain negative components, but the built-in ADC will not convert negative voltage. So we need to use a voltage divider made up of 2 bias resistors to rise the signal and making all components positive. The voltage between the 2 resistors will be coupled to the ADC input later. And I used 2 diodes to set up a clamp circuit. The protection circuit will provide over and under voltage protection to some extent to protect follow-up components from damage. There are 2 voltages required in our system. 5V DC from the USB port to supply the stereo headphone driver, and 3.3V DC from the voltage regulator to supply the microprocessor and other chips. The chip CH340G is used by the microprocessor to provide USB connectivity. RTS and DTR are connected to the reset pin and boot 0 pin of the microprocessor. A 12 MHz crystal and 2 oscillating capacitors need to be installed with it. The chip TDA1308 is an integrated Class AB stereo headphone driver working in a single power mode with positive 5V supply. It is used to amplify the low voltage signal from our microprocessor and improve the sound quality, clarity, detail, and dynamics. From the result, we can see that the processed signal has no negative components, while the phase and shape are the same as the original signal. For the headphone driver circuit, the frequency response curve for unity gain and 5 times gain are drawn. From the last test result, we can see that the gain is slightly attenuated when it's at very low frequency. But the frequency response of the whole system looks not bad. Limited by the sampling frequency of the ADC, we cannot restore the signal precisely when the signal frequency goes higher than 3.5 kHz. The original plan was designing and implement an FIR filter on the board, which can process and filter out random noise from an audio signal. However, the problem is that the final filter that I designed has more than 1,000 types. In other words, there are too many operations to get through at each sample, and it is far beyond our processing ability. To solve this problem, I used a bandpass filter to obtain noise with a specific frequency range instead of random noise. As you can see the difference from the spectrum of the original noise and the processed one. A low-pass filter is a filter that will allow signals with frequencies lower than cutoff frequency to pass, and attenuate signals with frequencies higher than a cutoff frequency. The first spectrum is a noised audio, and after passing the low-pass filter, as we can see from the second spectrum, most of the noise has been filtered out. Based on the system framework, I captured the schematic circuit diagram using KiCart. Power modules of all chips are placed on the top of the schematic. A debug header is connected to the microprocessor for late testing, and the schematic has been revised 4 times. The latest version is version 1.4. When it comes to the PCB designing, the first step is generate corresponding network tables based on the schematic diagram. The network table describes the electrical connection between all our components. All the circuits are placed near the edge of the board, and there's no right angle between electrical connections to reduce signal reflection. The final PCB is a double-layer board, and this is the 3D view of the board. It looks so good, right? In the implementation stage, first I ran a test on the board using a multimeter before connected to the power supply, just in order to avoid short circuit faults. Then the board was connected to my laptop by a micro USB cable. The next step was to set the DTR and RTX signals by CH340 to reset the microprocessor and execute the program. I used the macro instructions to complete the setting. In summary, the result outputted by the DSP kit showing a good denoising effect. The output audio from the speaker sounds similar to the original voice, and is straightforward to catch every word in the noised speech after processing. And I have also uploaded a demonstration video showing how the kit works. This is the timeline that I associated with each stage of my project, from last December to May. Thank you for watching my presentation video. Have a nice day.